Okay, to get started with number 1, let's just jot down some of the information that's given in the problem. We have the sample mean is 17. We know the population standard deviation is 1.76. The sample size is 25. And we want to know if the population mean is not equal to 16.2. When it says difference, that just means not equal to, and that's going to be in our alternative hypothesis. I might have said null a minute ago. The null, of course, will be equal to 16.2. And so here are our hypotheses. The null is always equal to, the mean, the population mean, always a parameter, is equal to 16.2. Again, always an equal sign, and then the research or alternative, you'll sometimes see that as HA, or in some texts you might see that as H1. Anyway, that's basically the question that's asked in the problem. Is the population mean different from or not equal to 16.2? So we will reject HO if the p-value is less than 0.05. That's always going to be a less than right here for our p-value. We're always going to reject HO if the p-value is less than whatever our cutoff is, and in the problem it said we want a 5% or 0.05 level of significance. So we're going to compute a z-test, and remember, for any hypothesis test, the test statistic, in this case a z-test, is going to equal whatever the statistic is, that's x bar, minus the hypothesized parameter. In this case, that's the hypothesized population mean. Remember, parameters are always what goes in the null hypothesis, or the null hypothesis and research hypothesis all concern population parameters. So when we're talking about means, that'll be mu, the population mean. We have the standard error in the bottom. This is just central limit theorem. We're talking about the distribution of a sample mean. So we'll have the population standard deviation divided by the square root of n. That's our standard error. So we just plug on in there. The sample mean was 17 minus the hypothesized mean of 16.2. The population standard deviation 1.76 divided by the square root of 25. And that'll give you 2.27. Of course, then we'll use that 2.27. We're going to use the z-table and find that to get our p-value. So we've got 2.27 from our z. We'll look that up in the z-table and get 0.4884. And that's the area from the mean to whatever point we have. In this case, it's the hypothesized mean, and the sample mean that we observed in this one was x bar. So our 0.4884 is right here. So in the tail, we'll have 0.5 minus the 0.4884, and that's how we'll get the 0.0016. There's a little bit more of a process here to get the p-value in this one. If this were a one-tailed test on the greater than side, that would be the p-value, but at the outset, our goal is to see if there's a difference from 16.2. And that could, of course, occur in either tail. And so we're looking at when we can see a difference. So in this direction, we have 0.8. And since this is a two-tailed test, we'll go 0.8 in this direction as well to get 15.4. Again, it was a two-tailed test, not equal to. We had 0.0116 in this tail, so we have another 0.116 over here. Again, those are the same distances. So our p-value is going to equal twice 0.0016 or 0.0232. And since that 0.0232 is less than 0.05, we'll reject HO and be confident that the population mean is not equal to 16. That should be 16.2. That's what's in our hypothesis. Even though the cups are designed to have 16 ounces, or that's what we're advertising, we're going to set our hypothesis a little bit higher than that because we want to make sure that we don't have customers who feel like they're not getting enough product for what they've paid. So again, this is just a repeat of what we had on the last page. We have a population mean hypothesized of 16.2, and we have sample mean that we found of 17, and we went the same direction over here. So since that was 0.8, this is 0.8. So 16.2 minus the 0.8 is the 15.4. And just reviewing again, we had 0.0116 on each tail. And that summed to 0.0232. So that is our p-value. And when we're going to interpret a p-value, we're basically going to put this picture up here into words. And what we're saying is if the population mean is 16.2, when we do our hypothesis test, we're in essence assuming that HO is true. So if the mean is 16.2, then there is a p-value chance, 0.0232 chance, that we would get either x bar greater than or equal to 17 or x bar greater than or equal to 15.4. Be careful on multiple choice questions because a lot of the multiple choice questions, or the distractors, will just leave this part out, and this statement isn't true without the conditional if at the front of it. Choice distractor will say there is a 0.023 chance and so on here, but without putting the conditional on the front of that. When we get p-values, what we're assessing when we get statistical significance, which we have in this one since we have a p-value less than 0.05, that just tells us whether or not the result that we had is likely or unlikely to be due to chance. That doesn't mean that the difference that we observed is important, that is of any practical significance, and that actually can be a problem, especially when you have a sample size that's large, because what you can end up with is, in a smaller sample, you might have something like this, and you're not significant until you get out here. And so if you get out here, you have statistical significance, and if you're over here, you fail to reject HO. But what happens if we take a large sample size? Let's say that this sample size was 25, and we take a sample size of, let's say, 100. Remember, we're going to have sigma divided by the square root of n. So if you divide 25 divided by the square root of n, you're going to get a larger number if you have an n of 100. That means that you're going to have narrower. So if you had a value, let's say, in here, at the smaller sample size, you would fail to reject HO. And by just increasing the sample size along, not the size of the effect, you would reject HO down here at that very same point. So we can say down here that at this sample size, a value out here is unlikely to occur by chance. We want to move beyond that to say whether or not that is an effect that's important, something that we really should pay attention to. And we do that with something called effect size. And though you really ought to interpret this in the context of the problem, in some cases a difference of 5 would make a real difference. In other cases 5 would make a difference at all in certain contexts. Well, what effect size is going to be, basically, in this context, there are other measures of effect size when we get into other contexts, is it's going to be the number of standard deviations, not standard errors, from the mean. And what we're going to say, I'm giving you some guidelines here, and these are some guidelines that were originally suggested by a fellow by the name of Cohen, and even he warns against this. This is guidelines that you might use when you don't know anything or know little about the context of what you're doing your research on. In the end, you should make these decisions more based on what you actually know about the situation where you're at. But anyway, we will use these in this class, and I'll give you a table that has those that you can print out and have available during an exam. So what we'll say is, this is even if it is statistically significant, if the effect is less than 0.2, we'll call that a trivial difference, not really important. If it's between 0.2 up to 0.5, we'll call it a small effect, 0.5 to 0.8 medium, and anything greater than or equal to 0.8 as large. And I've seen some things also that suggest actually 0.8 to 1.3, and then above 1.3 would be very large. But we'll leave it at this. So again, effect size is just, and we'll call it D, is just the difference between the sample mean and the hypothesized mean divided by standard deviation. So basically, instead of having sigma x bar on the bottom here, which is affected by sample size, we'll just put sigma. This is really what we've been doing before. Z is the number of standard deviations from the mean without correcting for n. But we'll use that here and call it D for effect size. And so, doing the math on this, we end up with 0.45, which, using the criteria from the previous slide, would be defined as a small effect. Okay, another way to look at parameters is to develop what's called a confidence interval. And you've seen these when you look at political polls. They'll say a candidate in the sample had 53% or 0.53 said they would vote for a candidate, but then along with that you'll see a margin of error. And if the margin of error was 5%, that means we're between 0.48, that's 5, minus 5, up to 58. Well, that 48 goes below 50%. And assuming we just have two candidates and everybody's made a decision, that has a different implication. So that would be called a statistical dead heat, or within the margin of error. A confidence interval will have statistic plus or minus margin of error, and that margin of error will always be computed as a confidence coefficient times the standard error. That confidence coefficient, I'll go ahead and tell you, will be either a z-value, or, we haven't gotten to this yet, but we'll have something called a t-value, and it might be that as well. This relationship here is a relationship you ought to spend some time making sure you know and understand, because if you've looked at the formula tables and there, you'll see that we have more than one statistic, not just x bar. We have p hats, x bar a's minus x bar b's, p hat a minus p hat b's, and r's. Well, all of those are going to have a statistic plus or minus confidence coefficient times standard error. So this will just be a general pattern that will work in a variety of problems, both on exam 2 and on exam 3, and for that matter on exam 4 and the final as well. So we have, in this case, the statistic is x bar plus or minus the confidence coefficient of z times the standard error, which sigma divided by the square root of n. And remember, we were comparing in this particular test to 16.2. That was our null hypothesis, was mu equal to 16.2, and h, or r, or 1, is mu not equal to 16.2. So our entire interval, 16.31 to 17.69, is greater than 16.2. Therefore, we can conclude that the population mean is not equal to 16.2. Now, one advantage you have with confidence intervals is you can test other hypotheses as well we could, based on this same interval, we could ask, is the population mean less than 18? And we would say yes, because the entire interval is less than 18. Could we say that it's greater than 16.3? Yes, because the entire interval is greater than 16.3. Could we say it's greater than 16.32? And the answer would be no, because the entire interval is not greater than 16.32. Could we say it's less than 17.68? And the answer is no, because the entire interval is not less than 17.68. So, we'll conclude, based on both the z-test, the z-interval, and the effect size, that we are out of control and that some adjustment needs to be made to the machine, even though it's only off by a small amount. If you're a wasting product, in this case, we'd say it's too high. At any rate, the entire interval is greater than 16.2. We're putting too much Coke in the machine, so we need to adjust the machine. At least that's one option here, to bring the amount of Coke that we're putting into the machine a little bit lower. Pay attention to in this problem is that interval that we had, that 16.31 to 17.69, that's really a wide interval. That is not only our interval for the mean, but remember that our standard deviation was 1.76. So if we were looking at individual Cokes and we went the mean plus or minus 2 of these for 95%, that means when you put in an individual machine, you're getting a pretty wide interval of possible individual values. Looks like it could be a range of about 7. That means you really don't have a very good machine itself. Not only do we want to be concerned with adjustments to the mean, and we won't do this in this class. If you go on to take a class in operations management, and you're going to look at something called statistical process control, it's not only going to be concerned with the center, you're going to look also at variability. And in this case, it looks like our machine is not tight in its tolerance limits. So we might want to do some experimentation and improvement instead of just looking whether or not we adjust the machine as it is. We might want to do some experimentation and improvement of the machine itself. I think we maybe have a more serious problem than just being off on the average. Okay, that'll be it for this presentation, for this problem, and